Hey, Chem 30s, it's Manchak here with the second half of this week's concepts, which is concept D5. So at this point, what you should have done is you should have gone through the video lesson for D4, should have sorted out all of that stuff with water ionization and acid-base strength and made that link between acids and bases in equilibrium. And now we're going to jump into talking about what are called Bronsted-Lowry acid-base reaction equations, or blabries, as I like to call them. And we're going to get into talking about what that is all about and really refining our definition of acids and bases. You should have also completed the LSM 16.1c, just so you've had a little bit of extra practice with pH and pOH before we move on to the rest of the stuff. So what I'm going to do right now is jump into talking about blabries and what they're all about, and I'll run through what that acronym is again. I just made that up and it's kind of dumb, but it sure is better than writing out Bronsted-Lowry acid-base reduction reaction equations. Sorry, Bronsted-Lowry acid-base reduction equation. Reaction equations. I can't even get it right. I'm sorry. I probably, clipped my mic there with my excitement to try to get that out of my mouth. Okay, so defining acids and bases is what we're going to cover according to what we call Bronsted-Lowry concept, and we'll talk about proton transfer as the mechanism for that, and then we'll be able to predict reactions that involve acids and bases and be able to write I'm going to get this right, Bronsted-Lowry acid-base reaction equation, or blabry. There are, again, those videos that I highlighted in the last video, the video that I highlighted in the last video, that you guys can go through that'll help to fill in blanks if anything didn't make sense. And the way I'm going today, who knows? And then you guys will have another worksheet, 16.2e, of your line masters to work on as well, which is basically getting some practice with these Bronsted-Lowry definitions before we move into D6, which is next week. That's going to have us doing a little bit more complicated stuff. So I'm going to click on this and we're going to get started. So we're going to get into talking about Bronsted-Lowry and what they came up with. And what's really cool about this, a little bit of background, is they actually I'm going to look back and then we'll look ahead. Hang on. So that was really weird. We have revised and revised again our concept of acids and bases, and it's working relatively well based on what we, pun intended, on what we learned in Chem 20, except there's a couple of things that don't work for us. One of the ones is what happens if there's no provision in what we know from modified Arrhenius that for a reaction that does not occur in solution. And then the second thing is some substances act to be both acids and bases in a chemical reaction, and that is kind of odd because something can be an acid and something can be a base. Here's an example of this: sodium hydrogen carbonate, the stuff that is baking soda. Okay, when we put it into water, it raises the pH of water. Raising pH means it's basic. Okay, so there's something in the sodium hydrogen carbonate that makes that solution with water basic. Okay. But when we put it into a solution of sodium hydroxide, it partly neutralizes the sodium hydroxide. Sodium hydroxide is a strong base. For some reason then, and here's the reactions. Here's our hydrogen carbonate ion. The sodium's not playing in this one. Reacting with water, it forms an equilibrium that basically does a little bit, that produces hydroxide ions. There's the evidence that we said at the end of Chem 20 that this is something that is basic. So this is the reaction with water. We get something that is basic. However, if we take those hydrogen carbonate ions and we dump them into a solution, I forgot a little negative there. If we dump them into a solution of hydroxide ions, which is basic, what we end up doing is establishing an equilibrium where we have water as one of the products. And remember, a neutralization is characterized as having water as one of the products. So there is some neutralization that has taken place here. So in this first example, the hydrogen carbonate is pretending to be a base. And in the second example, the hydrogen carbonate is pretending to be an acid. Really strange. Luckily, Bronsted-Lowry is going to help us out with this. So, in 1923, this is really cool, 2 European scientists independently developed a new approach to looking at acids and bases. And what that means is Bronsted was working on it, and Lowry was working on it, and they were both trying to define what acids and bases are and how to make them work, how to make everything make sense. And independently of each other, they both came to this more or less this exact idea. So they focused on the role that's I don't know, that's cool to me because not a lot of that stuff happens anymore because of communication and all of that stuff around the world. The nature of science has changed in the last 100 years, and so how information is transferred, all that kind of stuff. If you're bored someday, take a history of science class. I think you'd find it really interesting. Anyway, they focused on the role of acids and bases, and this is really cool. Let me just highlight that for you. In a reaction. Okay, what that means is they're looking at everything from the perspective of these entities being involved in reactions rather than just the properties of what happened afterwards. So Arrhenius often took us to the point where, hey, we know that if we mix these two things, what we end up with is something that is basic. Well, these guys said, well, whoa, let's back it up a bit. What's actually going on in the reaction? What's taking place? So here's what they suggested happens. In a case where we've got a strong acid like hydrochloric acid reacting with water, so we're dissolving hydrochloric acid in water, we can look at it that way. We say that the hydrogen chloride or the hydrochloric acid donates a proton to the water molecule. So what it does, and this is important. This proton word is important, and this word donates is important. Okay, and we're going to see that, and that produces then a hydronium ion and a chloride ion. And that means that we've created something that is acidic. In the case where we're taking a weak base in this case, which is the ammonia molecule, and we're taking the ammonia molecule and mixing it with water. In this case, what happens is we get hydroxide and ammonium ions. And what they're saying is that instead the water is donating a proton to the ammonium or ammonia, or the better way to put this is the ammonia is accepting a proton from the water molecule. So proton and donating and accepting. Okay. What's really interesting though, look at ammonia here. It is acting as a base. It's also acting as a base here. So we've got our hydronium ions that are being mixed. So we've got the solution we created up here and the solution we created here, and we're mixing them together. And we've got our hydronium ions and our ammonia, and we're mixing them together. And the hydronium is donating a proton, there we go, to the ammonia, and water is not part of the reaction. So they've looked at creating solutions of things that are acidic and basic or potentially acidic and basic, and then they've looked at how we can describe what's going on when something that is acidic and something that is basic reacts together. All of this you'll notice is proton, proton, proton. So this leads us to what we call the proton transfer concept, which is the idea that Bronsted-Lowry came up with, is that in an acid-base reaction, the thing that is the strongest acid donates a proton to the thing that is the strongest base. Okay, and the thing that is the strongest base accepts a proton from the thing that is the strongest acid. Okay, hope that kind of makes sense. So let's just define a few things here before we go on to anything different. So according to Bronsted-Lowry and what they came up with, a Bronsted-Lowry acid, okay, is something that is a proton donor. And I'll just define what a proton is in a second. A Bronsted-Lowry base is a proton acceptor. Okay, a Bronsted-Lowry neutralization is the competition for protons, where the strongest acid transfers a proton to the strongest base. And a Bronsted-Lowry reaction equation, okay, or what I would call a BLABRI, is an equation written to show the acid-base reaction involving the transfer of a proton from one entity to another, from the acid to the base. So this does away with defining a substance as an acid or a base. Rather, we're talking now about entities or molecules that are being involved in a proton transfer. And that's what we're really interested in. We're going to play with this a little bit. So if it's a little foggy right now, that's okay. We'll get there. Don't panic too much about this. So couple of terms, and we're going to use these interchangeably, even though they are not exactly the same term, but our curriculum says that we can use these interchangeably. Amphoteric or amphiprotic. Basically, we're describing something that is able to both donate a proton and accept a proton. And up here, our example of water would be something that is amphiprotic or amphoteric, because it can donate a proton as it did here, or it can accept a proton as it did here. So it behaves as both an acid or a base, depending on the situation you put it in. That should sound a little bit like what we did in Unit B, where we were dealing with entities that could either accept or donate an electron, right? They were either an oxidizing or a reducing agent, right? Do you remember that? Okay. So the advantage of the Bronsted-Lowry definition is that it enables us to define acids and bases in terms of chemical reactions rather than simply as substances that form acidic and basic solutions. Okay, that's the advantage of this, is we can really look at something and it has a lot of predictive power, is what we're doing with this concept. So I want to just go back here to look at these again, because there's something I don't know. I know I didn't point it out, and I don't know if you guys have picked up on it. And I'm just going to change the color of my pen here just to make it stand out a bit. So when we're talking about a proton in this case, we're talking about a hydrogen ion. Okay, and why we're talking about a hydrogen ion as a proton is, if you recall, and I'm going to really poorly draw this. Why did I put that in the middle? Proton. Hopefully that looks like a P to you. In our nucleus of our hydrogen atom, there is a proton. And then in the first energy level of our hydrogen atom, there is electron. Okay, if we get rid of that electron and we ionize the hydrogen molecule or hydrogen atom, basically all we're left with is a proton. So we're considering an H plus to be a proton. If we're considering H plus to be a proton, okay, if we look at these reactions, what I would call blabries, is we're getting the transfer of a proton, right? If you see HCl, we said, is donating a proton. We're transferring a proton. So there's a hydrogen ion going across. And that kind of makes sense, because HCl is losing a hydrogen ion, and it turns out to be Cl minus, right? There's no H left, and we took away a positive. And water is accepting the proton from HCl, so it is gaining an H and a plus. So now it is H3O, and it has that 1 plus. Same thing over here. If we're donating a proton, so the hydrogen ion is going from water to the ammonia, then what's happening is the water is going to lose an H and a plus, so it's going to turn into OH minus. And it's going to gain it, and the NH3 is going to gain an H and a plus, so it's going to turn into NH4 plus. Same thing down here. The proton is being transferred. Okay, so we've got H3O plus donating a proton, so it's going to lose an H and a plus, so it becomes H2O. And the NH3 is going to gain an H and a plus, so it becomes NH4. That's the transfer of a proton. And for now, I think as you guys move through these concepts, I would like you to actually show this to me. What is really good about this, for those of you that hate balancing equations, is that as soon as you transfer that proton, it's balanced. And this is a 1-to-1 to 1-to-1 ratio all the way through for these. It's really nice, because the only thing that's going across is a proton. And so we don't need to fiddle with any balancing as we move forward. So the next thing I need to define with you guys in here is what we call conjugate acids and bases, and what those are. And this is actually really simple. Okay, according to the Bronsted-Lowry, acid-base reactions involve the transfer of a proton, which we just talked about. Okay, and these reactions are universally reversible. I love that, and always result in an acid-base equilibrium. Okay, so we're going to always be watching for that particular notation that we have in the reaction. And so in this case, this is a reaction that we have here between acetic acid, which is our acid, and water, which is pretending to be a base, and our what things turn into. So we're transferring from our acid a hydrogen ion to the water. So the acid turns into CH3COO, and we're always going to lose the H off the end of a COOH. okay, whatever it is. If we have an organic acid somewhere, we're always losing the H off of the COOH in that organic acid. So we're left with the acetate ion here. And then water is gaining an H+, so that means we're going to have an H3O+ when we're done. So here's where we get into the conjugate stuff, and it's kind of like we're conjugating verbs. That's sort of where this is coming from. So if you've ever taken another language, you might understand how that works. I'm not going to get too deep into it, but here is our original acid. This is its conjugate base. Because if we look at this in the reverse reaction, if we're reading this from right to left instead of left to right, then this base right here turns back into an acid. It's pretending to be a base in the reverse reaction, whereas this is an acid in the forward reaction. So this is its acid and its conjugate base. Water is the base with its conjugate acid. So if we're reading this in the reverse, then the hydronium ion is now the acid, which transfers a proton to the acetate, which brings us back to here. This is the acid with its conjugate base if we're reading in reverse. This is the acid with its conjugate base if we're reading in the forward reaction. Hope that makes sense. Okay, so those are conjugate acids and bases. So based on the above equilibrium, in the forward reaction, the proton is transferred from acetic acid to water, and in the reverse, the hydronium ion transfers a proton to the acetate ion. In all acid-base reactions, there will always be two acids and two bases, and each pair differs only by one proton, so it's really easy to balance. We call pairs of acids or pairs of substances whose formulas only differ by a single proton conjugate acid-base pairs. Okay, so this and this, maybe I'll highlight it just so it's obvious to you. Acetic acid and the acetate ion are a conjugate acid-base pair. And then just to go to the different color, the water, right, and the hydronium ion are another conjugate acid-base pair. Cool? So now we need to bring in the ideas of strong acids and bases again. The stronger the base, the more it attracts another proton, the more it wants to take a proton because it becomes more stable at that point. And the stronger the acid, the less it attracts its own proton, meaning that it wants to give up its proton. It wants to get a little bit more stable as a result of that. So we can generalize this idea as saying the stronger the acid, the weaker its conjugate base, and conversely, the weaker the acid, the stronger its conjugate base. Okay, so that's important to know. And we're going to get to a table in a second here that helps to explain this. Okay. So here are some Bronsted-Lowry acid-base definitions, and I just took this summary out of your textbook. If you wanted to have a look at that at some point, you can. I'm not going to go over those because we've just gone over them. Don't forget, though, we do have our table of relative strengths of acids and bases on pages 8 and 9 of your data booklet. Make sure you've got this handy and open as you're going through this next section. So the last thing that we're going to do here is we're going to come up with a way that we can predict a predominant acid-base reaction. So let's say we're doing something new we've never done before, and we're mixing some chemicals together to see what's going to happen, and we want to predict, or we've done it maybe, and we want to predict what the results are going to be or how things are going to end up. So we are going to follow a 5-step method to do this. This probably sounds a little similar to some of the stuff we did in Unit B in the electrochemistry unit, so this shouldn't be too weird for you, I hope. The procedure we're going to follow to figure out what the Bronsted-Lowry acid-base reaction equation is, that's our goal of all of this, is we're going to follow these steps. First, we're going to list all the entities, atoms, ions, molecules, including water, that are initially present in the aqueous solution when we mix the two things together. Then we're going to label things as acids and bases. I hope this sounds really familiar. It's kind of a similar procedure. Using our Bronsted-Lowry definitions, this table will help you out a bunch if you want it to, because you can go through and anything that is in the acid formula column is considered to be an acid, and anything that is in the base formula column is considered to be a base. Remember, please, that some things can be both an acid and a base, like water, or something can be an acid and a base, like the hydrogen sulfide ion. Right here it is as an acid, and here it is as a base. Okay, Couple of other things I want to point out about this, and we'll get into this a bit later on, but remember our strongest acids are up here. These are our strong acids. And as we move down the table on the left-hand side, we get weaker and weaker acids, where we hit water, which is our weakest acid. Okay? And then over here, this is our strongest base, down in the bottom right. This should sound a lot like the relative strengths of oxidizing and reducing agents, I hope. This is our strongest base, and as we move up, we get to weaker and weaker bases until we get to water, which is technically our weakest base. Okay. Once we identify the acids and bases, then we have to identify the strongest acid and the strongest base. Okay. Once we've identified those, we write an equation showing a transfer of a proton from the strongest acid to the strongest base. Okay, and then we're going to predict the conjugate acids and bases. You can do that really easily here. If this was my, where did my page go? If this was my strongest acid here, then its conjugate base is whatever this is over here. If this was my strongest base, this is my conjugate base, or conjugate acid, pardon me. So acid, conjugate base, base, conjugate acid. And then we predict the approximate position of the equilibrium using the generalization. And the generalization is this. I know we didn't do the lab, but the generalization is if the strongest acid is above the strongest base on the table, the products are favored. Okay. If the strongest acid is below the strongest base on the table, then the reactants are favored. So if we go back to here, this is my strongest acid, this is my strongest base. Strongest acid is above strongest base, so the products are favored. If this is my strongest acid and this is my strongest base, then strongest acid is below the strongest base, so the reactants are favored. That's really how it works. Okay, so you can walk your way through these next examples using these five steps. And if it gets confusing, just track me down. But I'm going to do one example with you, and then I'll leave you the last example to do on your own and try it out. Okay, so just a couple of things before we get into doing the examples, which are coming up here. So water complicates a few things in these reactions. Specifically, so we need to make some assumptions or restrictions when dealing with these reactions in aqueous solution. So first off, the hydronium ion is the strongest acid entity that can exist. A stronger acid than hydronium is dissolved in water. It reacts instantly. So we think it to be hydronium. So if on your table of relative strengths, if you have any of these ones up here, okay, consider them to be a hydronium ion instead. They have turned 100% into hydronium ions. The second thing is that the hydroxide ion is the strongest base that we can have present. Okay, if a stronger base than hydroxide is there, then we're going to just consider that it reacts instantly into hydroxide ions with water, just like we did before. So, for example, and I've never seen it come up, but maybe it would. Sodium oxide is very strong base, right? So that sodium oxide will just turn into hydroxide, and we'll just consider it to be hydroxide. All right, let's try to get this done. No entity in an aqueous solution can react as a base if it's weaker than water. That's what I said a few moments ago. None of these are considered to be bases. So if you're on the base side and you're going above water, none of these are basic. Okay, so water is your weakest base. One last thing. In your questions, watch out for clues that the acid-base reaction you're dealing with is complete or quantitative. Watch out for those words, and it will tell you whether you need to write the equation with a single arrow or that double equilibrium arrow as we move forward. All right, I'm going to set up to do this example with you guys, and then I'll leave you to that last example on your own, and I'll wrap things up. Okay, so I'm going to set things up, and I didn't have things quite as ready as I wanted to, so this is going to be a little embarrassing for me. All right, here we go. All right, so let's run through this then. Here's your first example. What will be the predominant reaction if spilled drain cleaner, which is sodium hydroxide, is neutralized with vinegar, and are the reactants or products favored? So this is where we're going to list entities, write down acids or base, determine our strongest acid or our strongest base, and then write out our blabbery according to that. So First thing we need to remember, sodium hydroxide, remember when you have an ionic compound, it dissociates in solution. So we would have sodium ions and hydroxide ions. Sodium is neither acidic nor basic, so we're going to ignore it. But we know that hydroxide is a base. Okay. The next thing we have is our acetic acid. In the name, vinegar, acetic acid, it says acid, so it's probably an acid. So I'm going to list it as an acid. I said acid a lot there. And then we remember we always have to list water as well. Okay, so water can behave as both an acid or a base. And remember, you can find it on your table as an acid or a base. And so then what we're going to do is determine what is our strongest acid. Our strongest acid is going to be the one that is furthest up on the left-hand side, and our strongest base will be the one that is furthest down on the right-hand side. So there's nothing stronger than hydroxide, so that is our strongest base. We will find acetic acid right here on our table, and water as an acid is down here. So because the acetic acid is up higher, then it is going to be our strongest acid. So we'll label it as that. Then we're going to construct our Blabry. Okay, so it is our hydroxide ions reacting with our acetic acid. It's going to establish an equilibrium, and we'll deal with that in just a second. And that equilibrium is going to be, or what it's going to establish with, remember, your strongest acid donates a proton to your strongest base. So there is a proton coming across from your strongest acid to your strongest base in this reaction. So that means that your strongest acid turns into its conjugate base. And I know you guys can't read that, but its conjugate base is CH3COO. And your strongest base turns into its conjugate acid, which in this case is going to be H2O. Okay, that's our Blabry. That's really easy. At least I think it is. And if you're not sure of, what your entities are going to turn into on here, you got this table to kind of cheat off of a little bit, but you're just transferring a proton. That's really all that's happening. So the last step then is, are the reactants or products favored? That's what the question is asking us to determine as well. So remember, we said that if your strongest acid is above your strongest base, it favors the products. If your strongest acid is below your strongest base, so I should have done it that way, then it favors the reactants. Well, here is my strongest acid right here. There's my strongest base. My strongest acid is above my strongest base. So that means we're going to write up here greater than 50%. That means that it's favoring the products, if you recall thinking back to D2. Hope that made sense to you. Relatively straightforward stuff. This has created a Blabry for us. So if I ever ask about a Bronsted-Lowry acid-base reaction equation, this is a Bronsted-Lowry acid-base reaction equation. Cool? All right, so here we go. I'm going to leave you guys to finish off this example yourself, just so you are aware. The answer to it is at the bottom of page 730 of your textbook. If you'd like to have a look at that, I would encourage you to do so after you've done the example on your own. That is it for concept D5 and D4, but I've just done D5 in this video. So at this point, you guys have finished this week's worth of video lessons. I hope I wasn't too terribly boring. I hope I didn't trip over my mouth too much. I hope you got something out of it. Just a reminder, please go and do, now that you've finished this video, go and do 16.2E as some practice to get you ready for the practice quiz. Once you've done the practice quiz, please wait for some feedback from me before you jump onto the summative quiz. That's all I have to say with you about D4 and D5. Remember, next week is our last week of concepts that I have to teach you. Holy beep, you've made it through Chem 30. Wow. Okay, you are so close. You're almost there. Stay healthy and stay safe until then, and we will talk soon in concept D6 and D7. See ya.